Here we have question number 4 from the review. Question number 4 is similar to question number 3. Find two power series solutions of the given differential equation about the ordinary point x equals 0. And we have y double prime minus x plus 1 times y prime minus y equals 0. So we want power series solutions. We're going to let y equal the sum as n goes from 0 to infinity, c sub n x to the n. Then we get y prime is the sum as n goes from 1 to infinity, c sub n times n, times x to the n minus 1. And y double prime is the sum as n goes from 2 to infinity, c sub n times n minus 1 times x to the n minus 2. We'll substitute into the equation, and that will give me the sum as n goes from 2 to infinity, c sub n times n minus 1, x to the n minus 2, minus x plus 1 times y prime, which is the sum as n goes from 1 to infinity, c sub n x to the n minus 1, minus y, which is the sum as n goes from 0 to infinity, c sub n x to the n. And all of this is equal to 0. So 3 steps for combining summations. The first step is any x's that are outside of the summation need to come in and need to be combined with the x's that are already inside the summation. So notice on the second term, I'm going to change this to plus negative x minus 1, and then I'm going to distribute. So I'm going to take that whole summation and multiply it by negative x, and then multiply it by negative 1. Everything else will stay the same, so I'll just copy down my first term. And then on the second term, when I multiply by that negative x, I think what I'll do is I'll bring that x inside because I know I need to. So when I write my summation, I'll have the sum as n goes from 1 to infinity, c sub n times x to the n, because I'm adding a power of 1 where I have a power of n minus 1. Those ones will cancel. And then I'll have, when I multiply by negative 1, I'll just have the minus the sum, and goes from 1 to infinity, c sub n x to the n minus 1. Then I'll copy down that third term, sum, and goes from 0 to infinity, c sub n x to the n equals 0. So we brought our x's inside the summation. That was that second summation. Next, you want a common power of x. You want x to the k in each case. So if you don't have x to the k, like in this first case, we're going to make a substitution. In this first summation, we're going to let k equal n minus 2. Then n is going to be k plus 2. And when I make that substitution, I'm going to get k equals 0 to infinity, c sub k plus 2 times k plus 2 times k plus 1, x to the k. On the second summation, we're just going to replace n with k. So I get minus the sum, k goes from 1 to infinity, c sub k times k x to the k. On my third summation, we want k to equal n minus 1. So n is going to be k plus 1. And I get the sum k goes from 0 to infinity c sub k plus 1 times k plus 1 x to the k. And then on the last summation, k is equal to n. And we get minus sum k goes from 0 to infinity c sub k x to the k equals 0. Okay, so we brought all x's from outside of the summation to inside of the summation. That was step 1. 2, we formed a common power x to the k. That was step 2. Step 3 is to look at the lower index for each summation, and those need to be equal. If they're not equal, we need to remove terms from specific summations in order to make the lower indices match. So let's see. I have k equals 0, k equals 1, k equals 0, k equals 0. It would be nice if I could work backwards because 3 of these have matching indices. But we can't work backwards. We can't, if we're starting at k equals 1, I can't really work backwards to get to k equals 0. So from all of these k equals 0 summations, we're going to remove that first term. By removing that first term from each of these summations, we'll be able to write the lower index of the remaining terms, starting with k equals 1. So let me move up just a little bit. And on this first term, I'll write my k equals 0 term is c sub 2 times 2 times 1 x to the 0 plus, and then I can rewrite my summation starting now at k equals 1. K equals 1 to infinity c sub k plus 2 times k plus 2 times k plus 1 x to the k. My second summation was fine, so I'll just copy that down. Forgot my k. Sum k equals 1 times to infinity c sub k times k x to the k. On that third summation, we're going to take out the k equals 0 term, and that's going to give me c sub 1 times x to the 0 minus, and then I'll write the remaining terms with a lower index of 1. Sum k equals 1 to infinity c sub k plus 1 times k plus 1 x to the k. And then I'll start down here for my last term. I've got another k equals 0 term, and that's going to be minus, maybe I can fit that. This is not much. I'll just zoom in a little bit. Minus c sub 0 x to the 0. That's my k equals 0 term. And my remaining summation will be k equals 1 to infinity c sub k x to the k. All of that's equal to 0. So I'll zoom out so we can see all of this. Pretty much all of it. There. So take a breather. So next, all of those k equals 0 terms are going to be combined at the front. And then all of those summation terms are going to also be combined. So let me combine all of these k equals 0 terms. This first term is just 2c2. I'm going to put that in parentheses. 2c2. The second term is minus c1. And this last term is minus c0 plus all of my remaining summations have the same lower index, k equals 1 to infinity, and they have that common x to the k. So I'm going to factor out the x to the k, and that leaves me with c sub k plus 2 times k plus 2 times k plus 1 minus c sub k times k minus c sub k plus 1 times k plus 1 minus c sub k. All of this is equal to 0. So everything inside the parentheses is going to give me my recurrence relation. And actually these terms in front also give you part of the recurrence relation because they give you a relationship between the c's, between the coefficients of the power series. So because everything is equal to 0, we know that 2c2 minus c1 minus c0 is equal to 0. And from here, I'm going to solve for c2. Always solve for the higher index. 2 is higher than 1 or 0. And that tells me that c2 is c1 plus c0. Bringing those terms over makes them positive. And then divide by the coefficient of c2. Divide by 2. So I'm going to box that. So I know that c2 is c1 plus c0 divided by 2. From inside of the summation, if I solve for my higher index, which is the k plus 2, then all of these other terms, these 3 terms, that's all one term, will go to the right side of the equation. So I'm going to have c sub k plus 2 equals, then bring this negative c sub k times k over. It becomes a positive. Bring that negative c sub k plus 1 times k plus 1 over. That becomes positive. Bring the c sub k over. That becomes positive. And then divide by the coefficient of c sub k plus 2. K plus 1 times k plus 2. This is true when k equals 1 to infinity. So 1, 2, 3, and so forth. We might be able to simplify there. Let me see, what did I do? I forgot the 1 here. But notice that we do have like terms in the numerator. These 2 terms, c sub k times k plus c sub k, we can factor out c sub k. That gives me k plus 1. And now I have a k plus 1 in common. That I could factor it and cancel, or I could just cancel here. All those k plus 1s cancel. And that leaves me with C sub k plus 2 equals C sub k plus C sub k plus 1 over k plus 2. That's much nicer. K goes from 1, 2, 3, and so forth. So I'll box that up. And now we're going to find, we'll find 6 terms. X to 0 to x to the 5th. So coefficients would be C sub 0 to C to the 5th. Our terms are C0 x to the 0 plus C1 x plus C2 x squared plus C3 x to the 3rd, and so forth. This recurrence relation here is defined starting when k equals 1. So I'm going to start with k equals 1 and substitute in here. I get C sub 3 is equal to C sub 1 plus C sub 2 over 3. So this might get a little bit messy. Notice that up here we have C sub 2. So I'm going to rewrite this as 1/3 C1 plus 1/3 C2 so that I can substitute that in, and I get 1/3 C1 plus 1/3 times C2, which is, I guess I have to write it as 1/2 C1 plus 1/2 C0. When I distribute, that gives me 1/3 C1 plus 1/6 C1 plus 1/6 C0. And let me just rewrite it here. So we get C3 is 1/3 C1 plus 1/6 C1. If I multiply 1/3 by 2 over 2, that gives me 2/6 C1 plus 1/6 C1, which is 3/6 or 1/2. So that's going to give me 1/2 C1 plus 1/6 C0. So the good part here is that I'm already at C3 and I only have to go to C5. So I only need two more coefficients. The bad part is we have fractions. So we just have to deal with them. K equals 2, coming back up here, we get C sub 4 equals C sub 2 plus C sub 3 divided by 4. So that's 1/4 C2 plus 1/4 C3. So notice we have C2 defined here. That's 1/4 times 1/2 C1 plus 1/2 C0 plus 1/4 times C3 is defined here, is 1/2 C1 plus 1/6 C0. So I'll bring that down to the next line. That gives me C4 equals, when I distribute by 1/4, I get 1/8 C1 plus 1/8 C0. Distribute by 1/4, I get 1/8 C1 plus 1 over 24 C0. And then combining my C1s, I'll get 2/8 C1, which is 1/4. And then combining my C0s, I'm going to have to multiply by 3 here to get 3/8 or 3/24 plus 1/24 is 4/24 or 1/6 C0. So that's C4. C4 is 1/4 C1 plus 1/6 C0. And we'll do one more. Maybe I have space here. K equals 3 will give me C5 right here equals C3 plus C4 divided by 5. So I have C3 and C4 defined. So I'm just going to factor out that 1/5 and do the 1/5 at the very end. And we'll do C3, which is 1/2, C1 plus 1/6, C0 plus C4, which is 1/4, C1 plus 1/6, C0. And that gives me, I think I can do this here, 1/5 times 1/2 plus 1/4 is 3/4 C1, and 1/6 plus 1/6 is 2/6 or 1/3 C0. So if I multiply through by 1/5, it's going to give me C5 equals 3/20 C1 plus 1/15 C0. So there, I'll go to a new page. And our solution, we have up to 5 terms, or up to 6 terms. Our solution is a power series. It looks like it has a constant term, and then an x term, an x squared term, x to the third, x to the fourth, x to the fifth, and so on. As many terms as you need. So we have, if I come all the way here, our lowest indexed term that we found was C2. So and everything else is defined in terms of C0 and C1. So I have C0 plus C1x plus, and then for C2, I'm going to use 1/2 C1 plus 1/2 C0. That's my x squared. And then for my C3, we have 1/2 C1 plus 1/6 C0. That's my x to the third. I'll go to the next line here. Plus, my coefficient of x to the fourth is going to be C4, which is 1/4 C1 plus 1/6 C0. That's x to the fourth. And then my x to the fifth term, the coefficient is defined by C5, which is 3/20 C1 plus 1/15 C0. That's x to the fifth. And then our series continues onward, but we're only going to list our first six terms. So this is our power series solution. We're going to group terms to get our two linearly independent solutions, one solution will consist of all of our C0 terms, where C0 is factored out. So I'm going to underline these as I go. I get 1 plus 1/2 x squared plus 1/6 x to the third plus 1/6 x to the fourth plus 1/15 x to the fifth, and that continues, plus my C1, and then I'll underline each of my C1s. I have 1x plus 1/2 x squared plus 1/2 x to the third plus 1/4 x to the fourth plus 3/20 x to the fifth, and so on. So my two linearly independent solutions are these solutions that are inside the parentheses. That's my y1 and my y2, or you might want to call them y0 and y1 to match up with the coefficients. Notice they are linearly independent because our y1 contains a constant term, and there's no constant term in y2. y2 contains an x term, and there's no x term in y1. That makes them linearly independent. You could also use the Wronskian to show that they're linearly independent. Anyway, this is problem number 4. And we'll see you with problem number 5. Bye-bye.